end the meeting. That's why. Anyway, so I think we start with the. So I don't know what the question I've asked about that. Do you have any issue what we have covered so far? Like if you remember it, then we can actually discuss about that right now. Anything? No. Okay. So like regarding the pure substance, we know that there are substances that we see around us, and a pure substance is defined as a substance that, upon changes of phase, it always keeps its chemical composition from one phase to the other. It will keep its phase same. I mean, chemical composition same, like water. Water, when you are actually in solid form. Can you hear everyone?
Yes, sir.
Yes, sir, we're hearing.
Yes, sir.
Okay,
Totally.
perfect.
Sir,
Okay.
not if someone cannot join with us. Yes, sir, I can.
Hello? Welcome. কাজ চলছে তো, হয়ে গেছিল, আবার দিলাম শুরু হয়ে গেছে। ওইটাতে ক্লিক করে আবার চলে আসবে। Hello. So the pure substance. So the pure substance. So the students, can you just mute all of your audio devices, please? The audios. Mute your audio.
All of
Yeah.
your audio devices.
Thank you. So I have started about the pure substance, but there are quite a few things I think you need to know about, because one is some ethics that you have to go through. Okay, there are some terms and conditions about this class. Okay, first of all, you cannot copy, modify, or reproduce, publish elsewhere, sell, upload, or post or distribute any of the lecture materials without prior written permission. Now, what we are actually giving the what the lecture is giving to you, you cannot actually record or take photos or modify anything of this of what we are actually giving it to you. Okay, don't modify, record without prior written permission. You are able to take the notes, but you will not record it. Okay, and you will not share it. Any, you will not share it with actually in the social media as well. Okay, and don't give it or transfer, distribute privilege to any third party. So the pure substance that we are talking about is actually a substance. Whenever it changes its phase, it doesn't change its chemical composition. Okay? Whenever it changes its phase, like let's say an example of water, we have, especially when I give an example, usually we go for the water first because the easiest way to give an example. Now, water as a solid form, it is an ice. Okay. Now, when it is ice, still the chemical composition is H2O. And when it goes, it becomes liquid, upon increasing the temperature, still the chemical composition is H2O. And then when you change it to actually in gaseous state like vapor, still it is as it consists of H2O, hydrogen oxygen. So pure substance, whenever you're changing anything like only we cannot change the chemical composition of that substance. So there are three phases, as we know, that's solid, liquid, and gas. And one phase that we discussed already, that supercritical state, critical, beyond the critical point. When we study pure substance, we'll see that what is critical point, what are the stages, and how they change from one to the other, how the changes occur.
কে রে এগুলা করতেছে বেয়াদব?
So I want to share one thing with you, like as you know that I always follow the book of Sangel. Okay, so so I'm sharing it. So you see that there is a figure that we see that the three different phases, molecules are relatively fixed in solid.
Sir, can you just mute everyone?
Let me try. No, oh, no. Audio setting. No, I cannot. Yes, I cannot. But when I have said, I send the invitation, I send that whenever everyone joins there, mute their microphone. But still, they can actually, this individual participant may actually, unmuted. Uh, Jarif, Ahnaf Jarif, Ahnaf Jarif. Ahnaf Jarif. I
স্যার ও
think
লগ
this
ইন
is like
করতে পারে নাই।
Ahnaf Jarif, Nafisat, I can see you. Ahnaf, you actually, I think these noises are coming from your side. These musics are coming from your side. And who else are here? Okay. Okay. Yeah. So the musics are coming from.
No, sir. I think I had a problem with my mic.
Okay, anyway. So I think shared a screen with you actually. The Sangels to see to show you about the what is pure substance. Uh, I think I have mentioned already that I usually follow for thermodynamics the Sangels um, and the thermodynamics and engineering approach. So, and by definition, pure substance that has actually a fixed chemical composition. So, whenever it changes phases from different phase to different phase, so it always keeps its own chemical composition. And as you know that we have actually three different phases usually, three different phases: solid, liquid, and gas. And in the solid phase, the the molecules of a substance is most densely arranged. Then whenever the temperature increases, whenever it changes from the solid to the liquid, they are they are having more loose, configuration comparatively. And then uh, uh, in gaseous state, it is most haphazardly uh, oriented. So that's why we are having uh, you know three different phases at three different temperatures, three different conditions basically I can say. So these are phases, and phase change process, how the phase change occurs. There are very practical situations where two phases of a pure substance coexist in equilibrium. So first of all, let's go and see a diagram. So if you see this screen, I think you can see the screen. If whoever actually having the video, if you see this, you can see actually. I just showed a figure TV diagram of heating of water. A water heating diagram of water, like from starting 1, 2, 3, 4, and 5. Three different parts are shown on this line. Vertical axis shows the temperature, and horizontal axis shows the volume. So everyone can see the video, right?
Yes, sir, we can see.
Yes, sir.
Yes, sir, we can see the video.
Okay,
Yes.
thank
Yes,
you.
sir, we can.
Okay, so
Yes.
so the point one, there are five different points shown on the green line. 1, 2, 3, 4, and 5. Okay, and they are actually already mentioned in the description of this diagram. First of all, if you see this figure, whenever you see this, actually the first point is compressed liquid from 1 to 2. Why it is called compressed liquid? Because 1 to 2, we are giving the heat to water, and actually at point 2, it becomes, uh, you know, the water at 100 degrees Celsius. And then from point 2 to 4, from point 2 to 4, it actually becomes saturated mixture, then saturated vapor at point 4. Point 2 is saturated liquid, point 4 is saturated vapor, and 3 is the saturation mixture. 2 to 4 basically is a mixture of a liquid and gas state of water. So from 1 to 2, we are having the higher temperature, but there is no gaseous phase, only the compressed liquid. And from 2 to 4, this change of phase occurs from 2 to 4, and between 3 is the saturation mixture. And beyond point 4, it becomes saturated vapor. There is no water particle present. I'm not sure who is actually giving that, who is trying to mark on my figure. I'm not sure who is doing that. Someone is actually using some. Who's writing on the screen, please? Who's writing on the screen? Please don't write on the screen because it makes actually me confused sometimes what I'm trying to say. Okay. So when it becomes 100 degrees Celsius at atmospheric pressure, water starts to boil, and then point 2 to 4, there is no rise in temperature, and then at point 4, all the water mass is converted to saturated vapor, and then upon increased heating temperature, see that at 2 to 4 it absorbs the heat, but there is no temperature rise, and temperature rises after point 4, so it becomes a separated vapor. So that's how the pure substance changes its phases. So there are some points that we need to know. Saturation temperature, saturation pressure. Like the temperature is the water starts at a given pressure, the temperature at which a pure substance changes phase is called saturation temperature. And you know that there are two things, as we mentioned in the class always. Um, Pressure, first temperature, then pressure. The two most important properties that you need to know: temperature and pressure. As thermodynamics, we need always actually temperature first, then the pressure. That's why first the definition is saturation temperature. At a given pressure, the temperature at which a pure substance changes its phase for saturation temperature, and similarly, at a given temperature, the pressure at which a pure substance changes phase is called the saturation pressure. So you can see that in the screen right now, the pressure atmospheric pressure is only 1.325 kilopascal. Saturation temperature is 99.97 degrees Celsius, and conversely, at temperature of 90, it's actually a precise temperature. We all know that the temperature is 100 degrees Celsius in most cases, but in actual case, it's 99.97 degrees Celsius. So now we need to know the property diagram for phase change of processes. This is the important part to know, because the phase change we will need to show in different, phase diagram. There is a diagram that we should. So this is the TV diagram of phase change for water. This is actually for water. TV diagram of constant pressure phase change process of a pure substance at various pressures. Just to show you when the pressure changes, how the behavior of phase change occurs. An example given here for water at subcritical and below atmospheric pressure, the line at the very bottom. This is actually below the atmospheric pressure, 0.01 megapascal. Next, we are having almost atmospheric pressure, 0.1 megapascal. And when we see the gradual increment of the pressure, Loyal. you please mute all of your microphones? I can hear the noise. Raihan Imon, mute your audio, please. Raihan, mute your audio. Thank you. Mahmoud Hassan. Mahmoud Hassan, mute your audio, please.
হ্যালো স্যার, হ্যালো
Hello.
স্যার। আহনাফ জারিফ ও উপস্থিত নাই, ওর নামটা অন্য কেউ ইউজ করতেছে।
I don't know who actually shared it with him. Someone have given this to him, I guess.
স্যার হয়তো
Then
আমাদের কেউ এন্টার
they
করে
are using.
নেমটা চেঞ্জ করে দিছে, স্যার ও ক্লাস এন্টার করতে পারেনি।
Okay. So get to Vivo 1906. Who is this student? Vivo 1906. Turn off your micro, mute your audio. Vivo 1906. So if we see that, like the so with increase in the pressure, we see that the length in the horizontal part is decreasing. You see the length in the horizontal part, that is this part from 2 to 4. In the previous figure we have seen that 2 to 4 is basically horizontal, and this is called the latent heat of evaporation. And at the temperature when it will absorb the heat to change the phase only, that is called latent heat of evaporation. And this segment basically decreases when at a TV diagram the pressure changes. See the change in pressure, the length of latent heat of evaporation part is actually decreasing from bottom to the top. At that point there is no latent heat evaporation. You see the point is already mentioned here. That is called the critical point on the top on 22.06 megapascal, and the temperature is mentioned 373.95 degrees Celsius, and that is the critical point of water. At this temperature and pressure, water is quickly converted to gaseous state, and there is no phase change, the latent heat of evaporation. So at some point, whenever we reach this condition for water, it is directly converted to gas. So the latent heat of evaporation, that means the temperature at which, at a given temperature pressure, the amount of heat absorbed by water to become gas from the liquid. This is called latent heat evaporation. And the opposite, the vice versa segment, you can see that whenever the gas is actually, the gas is the vapor is condensed at the liquid at the same temperature, this is called the latent heat of condensation. Same process but in opposite direction, that is called latent heat of condensation. That means we're condensing the liquid by reducing the temperature or pressure of a substance. That is called latent heat of condensation. And if we're converting the liquid into gas, that is called latent heat of evaporation. So this is TV diagram, and it shows various pressure lines. This is the constant isobaric lines, isobars, from below atmospheric pressure to beyond the atmospheric pressure, beyond the critical point. You see that there is a top pressure and temperature at which, upon increasing the temperature or pressure, the substance is strictly converted from liquid to gas. There is no intermediate phase. That is called the critical point at which the liquid is directly converted to gas. And this is actually on figure 316. That's the one I'm trying to say. The comparison. Say that below critical point, below critical pressure, and beyond the above the critical pressure, there is a phase change. You see that when the pressure is below the critical pressure, there is a phase change, uh, distinct phase change from liquid to gas, and there's this horizontal line in it. But when it reaches the critical pressure and temperature, it doesn't have any phase change, and beyond the critical pressure, it even try to move straighter compared to the subcritical phase of phase change. Now, these two figures that I should basically ponder upon. These two figures I always try to show, and I think I have shown these ones at some point to some of the classes, that PV diagram and TV diagram of pure substance. And if we recall the TV diagram having the constant pressure lines 0.01, 0.1, then 1 megapascal 8, and after critical point, then real critical point, you see that the sharp change points, especially. Uh, if you join these points, there is point one, the edges. If you join the edges of the phase change point, this is the point of saturation liquid and point of saturated vapor. If you join those points, then finally you'll get one of the figures like this on the left side, TV diagram. And anyway, so you see this, the line, solid line from on the left. This is TV diagram of a pure substance. So you see that there is it's a up to critical point. There is two lines. If you actually try to distinct two different phases, saturated vapor, saturated liquid, the left hand line is actually a saturated liquid line, and the right hand side is saturated vapor line. That means on saturated liquid line, all throughout this line, basically all the liquids are saturated. That means upon increasing heat, it will start to converting vapor. And the saturated vapor line is basically the line on which all the liquid has become saturated vapor, and in the middle this is saturated liquid vapor region, and the point on the left hand side of the saturated liquid line, this is called compressed liquid region, and the point of the region beyond the saturated vapor line is called the superheated vapor region. Okay, and it is constant pressure line. It actually increases from left to right, it goes upward, and on PV diagram you see this, the temperature line becomes actually, it goes from upward to downward. The same, the figure has the same, um, same appearance, and having it shows the critical point on the top. That means beyond critical point there will be no distinctive phase change process. Below the critical point it will have the saturated liquid vapor region, but beyond that there will be no such vapor liquid region uh, present in the system. The left hand side compressed liquid region, on the right hand side of the system vapor line is because becomes superheated vapor region. So you see this basically, I'm trying to say that this is the critical point, and this line from the left of the critical point, this is called a saturated liquid line. That means when we have started increasing the temperature of the substance at a given temperature pressure, liquid, when it reaches up to these points on this line, they become saturated liquid, and upon increasing further temperature it will, on not temperature, upon increasing the heat or adding some heat into it, it will become vapor, start to vaporize. And then on the right hand side, this is called the saturated vapor line. Okay, this is the saturated vapor line, and this vapor line, beyond this point, like all the liquid has been actually converted into vapor, and beyond this point, someone has already pointed out about like circling that in the blue color. It's called superheated vapor region. Okay. Now we have seen actually the phase diagram, PV and TV diagram. The PV diagram substance that there are another phase diagram we're going to see right now. PV diagram of substance that contracts on freezing, and PV diagram also that expands on freezing. And as you all know that usually water that expands upon freezing. So the right hand side figure, figure B, basically is actually for water, and figure A is for the other regular substances. And you see there is a line is common on these two figures. There is triple line. What does it say? Triple line. What is triple line? On this line, a substance may exist at three different phases at a time. That is called, the
Triple point.
triple line. That is called triple line. You see the definition here. This is called triple line. The triple phase state from a line, that is called actually triple line. Like under some condition, all three phases of your substance coexist in equilibrium. On pivot diagram, this point, the line is called triple line, and triple line appears as question PD, often called triple point. The triple point for water is actually this 0.1 degrees Celsius, 0 degrees Celsius, and 0.6117 kilopascal. Okay. So at a given condition, if we are able to bring the temperature 0.01 degrees Celsius and 0.6117 kilopascal, we are able to keep the three different phases of water, at a time. Okay, so that is called the triple point. Um, so I think and there's a table just to show you that is some, you know, that there are some substances who has this actually this type of triple points. So, and if you see that more distinctively of a pure substance, the PT diagram, and this is actually called, you see this uh, triple point, and so this is triple point, and see from origin to the triple point is got sublimation, and on left hand side this is basically solid, and this is actually vapor, and in the middle this is actually liquid portion of the system. So sublimation means, I think I have mentioned one of the classes about this, like when a substance is directly converted from solid to gas, from solid to gas, this is called sublimation. So, and the starting point of, you know, the phase diagram for two different substances, a substance that expands on freezing, then melting starts faster compared to at a lower temperature compared to the substance that has a contraction that contracts on freezing, and that's why you see that the dashed line is for the substances that expand on freezing, and the solid melting line is the substances those actually contract on freezing. So I think I can stop here, and I'll start the next class about some of the substances, some properties, and we'll start about the property table in the next class. And hope to see you in the next class again, I think. Okay. Hopefully by this time I'll be able to get access of the Zoom Pro account. Do you have any question? Who said that?
Assalamualaikum, sir.
স্যার সাবলিমেশনের ডায়াগ্রামটা একটু
Okay, just a second.
সাবলিমেশনের ডায়াগ্রামটা
Okay, just a second. This one?
ইয়েস স্যার
One?
Yes,
Okay,
sir.
so I think I skip one thing. Just one. So this is basically a sublimation. This is sublimation. Just, this is sublimation. Solid plus vapor. Okay. From here, this is sublim. Like there are some substances when we can actually those basically is converted from solid to gas directly. You know the dry ice carbon dioxide. It has actually two. We cannot get liquid carbon dioxide, either solid or gaseous. So that is called sublimation. Basically, when we are converting a solid substance to liquid, gaseous gas directly, having no liquid phase inside, this is called sublimation process. And the temperature at which the solid is converted to gas directly, that is called sublimation. Okay. Did you get the point already? This is actually more the you can see it from here as well. The letter of passing from solid phase directly into the vapor phase is called sublimation. This is
Sir,
actually
the graph
this
was
is
actually a bit
basically
confusing. Like, which part of the graph is showing that there is no liquid state of that, like, whichever substances we are using, sublimating
okay.
substance, which part of the graph is showing
Okay.
that there is no liquid state of that substance?
There's the chip. This one. See sublimation, solid and vapor, solid and vapor.
So if there
So
was
is
a
there any
liquid
liquid?
state, how would have been the graph? Like, if there was any liquid state, like it was not a sublimating substance, then how would have been?
Just a second, I'm showing you. So you see that this is solid part. Okay. This is solid, right?
Yes, sir.
This is vapor, and there is a liquid. This is you see the melting point. There are two melting lines. There is one here, the dash line, and there is a solid here, right?
Yeah, yeah.
This is dash line. This solid line. So triple point means where we are having the three different phases together. So from here, the phase actually getting more distinctive. So on the left hand side dash line, and it is actually the substances that expand on freezing, the solid melting line, this substance that contract on freezing, and the solid vaporization. That means this part is basically the liquid phase. From dash to the solid, this line, I should change the color. So from here to here, inside these two lines are basically the liquid phase, and below those two on left hand side, this is liquid and this is vapor. And this is basically here we see the liquid part in the middle from melting and vaporization. Okay, so in sublimation there is no other phase, no liquid phase. You see only solid and vapor in this. Okay,
Yes, sir.
still confusing?
No, sir. No, no, sir. It's alright.
Sorry.
No, sir. It's okay. Understood.
Okay, so I think I will stop here today, and the next class we're going to start in the, uh, the property tables. Okay, and then the importance of property to know the different properties. How can we get the properties from the table? And this is very important for air conditioning, the refrigeration system, and in calculating the boiler performance. Okay.
So, can you please share the book with us? It's like,
I have mentioned that it's online. It's a very big. Almost how? What is the? Let me see.
Sir, I have a final question.
Yep.
Sir, if you're listening.
Yeah. Yeah. Please go ahead.
Sir, what is
The,
the purpose of using a small v? Like its unit is like meter cube per kg. Like
It's called specific volume instead of the volume we have been using so far. Like
yeah.
only the
That's the thing. Yeah. That's the point. I get a good question. I mentioned that the next class I will start about those what are the I have only mentioned the some properties I'm going to go through.
yes,
So
sir.
we know that we know volume, but we don't know the property specific volume. Now if you see that
Yes,
we
sir.
know the volume is actually unit meter cube, right?
Yes,
The
sir.
unit of volume is meter cube. But the
Yes, sir.
unit you have seen that is meter cube per second. Sorry, kilogram.
Per
Meter
kilogram.
cube
Yes,
per
sir.
kilogram. So that
Yes, sir.
means that is the volume per unit mass. That is volume per unit
Yes,
mass.
sir.
So
Yes,
any
sir.
property in thermodynamics that is per unit mass in most cases,
Yes, sir. Yes, sir.
any property that is per unit mass, that is called specific property. That's why it's a specific
It's,
volume. That's
yes,
why
sir.
it is called specific volume. Okay.
Sir, can you
And
please
we're going to
repeat it
learn
again?
about.
So just this line.
Sorry.
So
Sir,
can you
so I
please?
can say that it's similar to specific heat.
No, it's different. Specific different.
No, sir.
Specific is
Specific heat is also expressed in terms of per unit mass. That's why. I mean, these are also like
kilo.
thermodynamic property.
No, kilojoule per kilojoule per kilogram degree Kelvin.
Yes, sir.
Okay. So that's different case. So the specific volume, that is volume per unit mass of a system, that is called specific volume.
Yes.
Okay. You can say that specific heat is actually the similar way, but there are difference. You see the unit of specific heat and specific volume. You check the unit of specific heat.
Yes, sir.
It's
One
kilojoule per kilogram, degree
per,
Celsius, I guess.
per degree Celsius or per Kelvin. Yes, sir. Yes,
Yeah,
sir.
that's the thing. Okay. So anyway,
Sir, I have a question. That
sure.
is it beneficial to use the specific amount in some way in
Yeah, but that is
calculating
per
or
unit mass.
deriving equation?
If that is per unit mass, you have to calculate for per unit mass, and then
Yes, sir.
when you're applying it for the system, if you know the total mass, then you'll get the total value of the property. If you're not getting the mass of a system, then still you will able to calculate the property per unit mass. That's why the property table is given per unit mass. And now if you want to get the total property, then you need the mass of the system. And if the mass is given, that's fine. If the mass not is given, then actually specific properties are okay with the system. Okay.
Yes, sir.
Sir,
I've
I
got
have
my
a
answer,
question.
sir. Thank you, sir.
Okay, thank you.
Sir,
Any more
sir, I have
question?
a question, sir. Sir,
Okay.
I have a question.
Okay. Yeah, carry on.
What does supercritical water produce when the temperature is low?
No, at low temperature and pressure, there is no supercritical, a point. The supercritical point is beyond actually the high temperature and pressure, 373.94 degrees Celsius for water and 22.064 megapascal. And it
Sir,
actually
then
super, yeah.
what does supercritical water produce when the temperature is higher than the?
It becomes actually a supercritical state. There is no, you cannot define the phase. That is the issue. You have three different stages, right? So phases:
Yes, sir.
solid, liquid, and
Yes, sir.
gas. But
Yes, sir.
beyond the critical point, the substance becomes supercritical. So
Yes, sir.
it is not a liquid, not gas. That's why it is called supercritical fluid. It's something in between is these two, or near to liquid. There is no distinctive liquid or gaseous phase of it. It becomes supercritical fluid. Okay.
Yes, sir.
So it used to chemical treating of some substances, and I think I mentioned that I have done my PhD thesis on supercritical water gasification to produce hydrogen. So
Yes, sir.
there are so many options to use it, especially for treating or upgrading some substance to useful products. Okay.
Thank you.
Any question?
স্যার
Yeah.
স্যার আমরা তো স্যার 100 জনের বেশি ক্লাস করতে পারতেছি না, তো ওই প্রবলেমটা কি করবেন স্যার?
I have
মানে
mentioned that
100 জন।
yeah, I'll send them email today again to remind them, and I'll try to solve this issue as soon as possible. Hopefully by the next week, inshallah, I'll be able to get the Zoom Pro account. Okay.
Yes, sir. Thank you.
Any more question? If not, then I can actually end the class. Okay. Okay. Thank you. Stay safe, and hopefully we'll see you in the next lesson.
Assalamualaikum, sir.
Assalamualaikum, sir.
Assalamualaikum, sir.
Assalamualaikum.
Assalamu alaikum, sir.
Assalamualaikum, sir.
Assalamualaikum.